Okay, so we'll officially get started with our Carbonyl chapter, or continuing with our Carbonyl chapter. The homework, like I said, is posted up there. I've got it broken down into a couple different categories. Nomenclature, which we talked about last week, and then looking at the three possible nucleophiles. Your carbon nucleophiles, nitrogen, and oxygen. The carbon nucleophile should stand out as kind of an odd one. Why would carbon stand out as an odd nucleophile? Not very likely that we can put a negative charge on a carbon atom. Okay, so those typically are fairly rare nucleophiles. They aren't as easy to make, so we do some interesting chemistry to make those. Okay, you'll also see some redox questions. A lot of the redox questions are things that you've already seen, using chromic acid or PCC with an alcohol to make a carbonyl, so looking at the synthesis of them. We'll add one more reducing agent. I think just one more. I forget which problems I picked. Instead of H2 and palladium or platinum, we'll look at one more that will react solely with carbonyls, not with alkenes. Okay, so not with carbon-carbon double bonds. Okay, and the last part of it is synthesis, looking at how you can start to put these individual reactions together to make an overall product. Okay, so just like you've been seeing with the past exams, individual steps. Okay, so what happens at each step to make the reaction progress forward? So what can you tell me about this functional group? Stupid stapler. So what chemistry do we have available to the carbonyl? This oxygen has some lone pair electrons. Not only does it have those lone pairs, it's also more electronegative than the carbon, which means the pi bond spends most of its time with the oxygen as well. So that oxygen can act as an electron donor. What kind of species are electron donors? We get our Bronsted bases and Lewis bases, and if we want to get extra specific, we also have nucleophiles. What other chemistry is available here? Our carbon, being bound to an electronegative element, has electron density being taken away from it, so that carbon can act as an electron acceptor. Which means we've got a Lewis acid. What else? We got an electrophile. What else? We did not take the bait. It's not a Bronsted acid. Why is it not a Bronsted acid? And we're not looking at hydrogen. Okay? So those are the general reactivities that we've got with our carbonyl. Okay? We'll expand that a little bit at the very end of the Carbonyl chapter, just because it'll be relevant for biochemistry, but it's a lot more complex and I don't want to deal with it this semester. Okay? So, last week we ended, we kind of summarized what was going on. We've got our nomenclature of our aldehydes and ketones. We've got our general reactivity, which we just addressed, and now we're going to take a look at the nucleophiles. Okay? How can we have each of these individual nucleophiles react with a carbonyl? What's the end result of each of those reactions? Okay? So the first one that we looked at was carbon acting as a nucleophile. We generate a negatively charged carbon, which is shown right there in the middle. In this case, we're reacting our nucleophile with what kind of a carbonyl? What functional group? I think it even says up there. Yeah, it does. We've got a ketone. How do we know it's a ketone? R typically is referring to some carbon-containing structure, so we're looking most likely at a ketone. Okay? So when the nucleophile reacts with the ketone, it donates its electrons to the electrophilic carbon. That electrophilic carbon then has too many bonds, and we have to break a bond. The easiest bond we can break when dealing with this mechanism would be the pi bond. So we take the electrons on that pi system, or in that pi bond, and we move those up to the oxygen. Okay? So the oxygen just gained a pair of electrons, which means it's now negatively charged. The carbon, what happened to the carbon? It lost electrons, so it should be positive, but there's no formal charge there. What else happened to the carbon? Also gained electrons from the nucleophile. So it starts neutral, loses electrons, gains electrons, overall result, still neutral. So we now have our neutral carbon with our new bond to our nucleophile. Okay. At this point, we could go through and try and evaluate the reactivity. Okay. We've got a negatively charged oxygen. That is potentially reactive. What does it need to react with? Something positive. Do we have anything positive in this structure? No. So what ends up happening? Nothing at this point. Okay. The reaction stalls and stops. Okay. We'll follow it up once the reaction has formed this oxide. We'll then move on to step 2, where we add a new chemical. So we let the reaction go for a while to generate our now blue boxed product. Once that's formed, our reaction has nothing else to do, so it just kind of sits there. We go through and finalize it by reacting it with something to neutralize that negative. It's the easiest thing that we can add to neutralize a negative? A positive hydrogen, which means we're adding an acid. In this case, we kept it generic, or I kept it generic, and we added H3O+. Okay? The oxygen can share its electrons with that hydrogen. Hydrogen would then have too many bonds, so we take the electrons in that hydrogen-oxygen bond, and we move them towards the oxygen. Okay? And we end up with our final product. We now have what functional group? An alcohol. What type of alcohol do we have? We have a tertiary alcohol. So if we start with a ketone and react it with a carbon nucleophile, also known as our Grignard reagent, we can generate a tertiary alcohol. Okay? Questions about any of that? Okay, what happens if we change our functional group? Instead of starting with a ketone, let's go through and make it an aldehyde. What would we need to do to make it an aldehyde? One of those R groups needs to become an H. And it would look awfully messy for me to just draw it over the top. So instead, I copied and pasted it, and I changed that R group to a hydrogen all the way through. That R group or hydrogen has no effect on the mechanism. The nucleophile still attacks a positive carbonyl carbon. Okay? So we still have our electrophile and our carbonyl. That bond still breaks. We still break the pi bond. The oxygen still generates that negative charge. Again, we now stall. We don't have a positive for that oxygen to react with. Once the reaction stalls, we add our second reagent, which ends up being our H3O+ again. We protonate the oxygen, and we end up now with, again, an alcohol. Except what's different about this alcohol? We now have a secondary alcohol. Okay? Copy paste. It's only going to get worse too. Because this is copy pasted once more. What if you want a primary alcohol? What's that? If we go back to our starting material, instead of that being an aldehyde, or instead of having an R group there, I want to have another hydrogen. Okay? So all we're trying to do is quickly change our starting material to adjust how that predicts different products coming out of this. So when we go through, we now have a slightly different group. And before you point out the copy-paste mistake again, we can start with something known as formaldehyde. Okay, is that necessarily a functional group? No, it's still technically an aldehyde functional group. Formaldehyde just happens to be that compound. It's one of the more commonly known aldehydes because it's used as a preservative and all sorts of other fun stuff. Okay? So if we started off our Grignard reaction with a formaldehyde, our carbon nucleophile could go through an attack, and we end up with a primary alcohol. Okay? Questions about that? Mechanistically not too bad, right? Kinda, sorta. Okay. So, whoops. So we could all put it all on one slide, and now you can see everything matched up and how it ends up changing our overall structures. Okay? So the intent is recognizing how the carbonyl can react with that negative carbon. The next problem is going to become, how do we make a negative carbon? Okay? And because the next slide actually gives away the answer, let's take a step back. Have we seen a negative carbon before? Yes. How did we generate a negative carbon before? We added a strong base to an alkyne. Okay? So we don't have to move into a Grignard reagent to generate our carbon nucleophile. We have seen it one other time, and that's looking at the alkyne, okay, a terminal alkyne. Just as a refresher, just in case people have forgotten, if we start with our alkyne, and we would refer to it as a terminal alkyne, let's draw it out like this. We're saying the triple bond is at the end of that structure, which means, actually let's draw how it would be initially drawn. Okay, we could call that our terminal alkyne. We're implying what atom? A hydrogen, so we can add that hydrogen onto it. What's special about that? Due to the hybridization of that carbon being sp hybridized, it's now increased in electronegativity, which means, what does it do to the electrons in the bond between the carbon and the hydrogen? Pulls them towards it. If we push that to the extreme, what's our result? We end up with a lone pair, hydrogen floating off on its own. And to finalize with all your structures, what do you need to do? Look for our charges to have a negative and a positive. So how can we remove or stabilize that H+? We need to give it something negative. In the case of the alkyne, if we just leave an alkyne by itself, the alkyne carbon, okay, this carbon ends up reacting with the hydrogen and goes right back towards our starting material, okay, right back towards our terminal alkyne. So we have to have something rip that hydrogen off and pull it away from the solution. So what do we add? You could draw it as NH2 minus, or if you wanted, you could add the sodium. NH2 pairs up with the hydrogen, and we end up generating NH3. If we went and just compared back and forth on this reaction, or carbon negative versus nitrogen negative, which one can hold a negative charge better? Nitrogen. So why would this reaction progress forwards? What's special about NH3? It's a gas. Okay? So when we run this reaction, once that's formed, it can evaporate out of the, or remove itself from the reaction. With it gone, there's nothing to force the reverse reaction. We don't have that hydrogen source anymore. Okay? If we look back to the exam, the exam started with, I think I'm going to get the structure right, this compound. What kind of triple bond is this? It's an internal triple bond. We still have that sp hybridized carbon. So we still have a more electronegative carbon on either side. Okay? So those carbons will absolutely still pull electrons away from the atom next to them. What's the atom next to them? Carbon. Is that a hydrogen? No. Does this species act as an acid? No. Okay? So if we add sodium amide to an internal alkyne, no reaction occurs because there's no acid. We might be adding a base, but it doesn't matter. There's no acid there for it to react. Nothing occurs. Okay? So evaluate the structures, particularly implied things that can show up. Okay? The reason we went back over this again, we generate a negatively charged carbon. We have a nucleophile. That acetylide ion could go through and attack and react with a carbonyl. Okay? So that's only one way to generate a carbon negative. So let's take a look at another option. Let's go through and take a look at Victor Grignard's reagent. I'm going to call him Victor Otto Grignard, just for you. Okay? So what he went through and did is he noticed that some organic materials responded oddly in the presence of some metals. In particular, magnesium was the one he looked at in this case. Okay? So if we're going to look at magnesium metal, how many electrons does a magnesium metal atom have? I know we don't have a periodic table in here. It might make it a little more difficult. It has 2 electrons. Okay? In general, we might consider that it has no electrons, that it's a +2. But when we refer to it as magnesium +2, is it magnesium metal? No, it's magnesium ion. Okay? So what he did was took the metal magnesium and mixed it with, in this case, benzyl or bromobenzene. Okay? So an alkyl halide. Okay? And he also had to use a very particular solvent, which we'll look at in a second too. He had to use something like diethyl ether. There are a couple other ones that do the same. Okay? And what they ended up, or he ended up predicting in the course of this reaction, is that the magnesium decided to share some of its electrons. But it shared it in kind of an odd way. Okay? It decided to share 1 electron. Okay? Bromine, being more electronegative, sees that 1 electron and says, I want to grab that electron because I can steal that entirely away. Whereas right now, in its current bond, it has to share with the carbon. Okay? So to do that, bromine's going to take its electron back from carbon and say, give that back, and it's going to share its 1 electron with the magnesium. Okay? And instead of writing this mechanism, I'd like it if you more think about it and ask questions about it. I'm not going to test specifically on the mechanism. Okay? How many electrons are in that bond between carbon and bromine? 2. How many electrons have we moved? 1. Okay? If this mechanism is going to be correct, we must explain where that other electron went. Okay? Bromine can't take it because then it would exceed its octet, which means that electron is going to stay. Okay, it's not going to just stay floating in air. That's extremely unstable. Something's got to pick it up. What's going to pick it up? The carbon, where it originally came from. So we'll move the electron back to that carbon. What's different and odd about this mechanism? We're moving one electron individually, okay, as opposed to moving a pair of electrons. How do you know we're moving one electron at a time? We're using half an arrowhead, okay? So what we're looking at is what's referred to as the set mechanism, or single electron transfer, okay? So what's the result of this? Okay, and I've noticed a lot of people are still having problems with drawing out mechanisms. We draw the arrows first to signify where the electrons are going to move. Then we draw the products of those of the electrons moving. Okay, so if we take a look at this, the bond between the carbon and the bromine, what happened to it? Is it there anymore? No. Okay, so we won't show that bond anymore. We're showing electrons between bromine and magnesium. We're showing 2 electrons occupying the space between those 2 atoms, meaning we've formed a bond. Okay, so we now have a bond. That is technically in blue, although I'm not sure you can see that. Okay. Magnesium still has 1 electron left. We haven't touched that yet. And the carbon still has 1 electron left. Okay. We said that 1 electron in that bond went and sat on the carbon. Okay. What we've generated here is known as a radical, okay, or a free radical. So if you hear any health effects about free radicals or free radical oxygens in your blood, this is what they're talking about. Okay. It's an unpaired electron sitting on an atom. Okay. The fun thing about radicals, or the not so fun thing about radicals, is they are extremely reactive. Why would they be reactive? They're not paired. Okay? We get stability from pairing of electrons. If we don't have them paired, they're going to try and react with anything they can and try and pull electrons off of something else to stabilize, to pair up and form an individual bond. Okay? Which is one of the reasons why they're incredibly dangerous when we're looking at biochemistry or our biological systems. If we've got free radicals in our bloodstream, those compounds are grabbing electrons from every source they can possibly get. In a process of grabbing an electron, what do they end up generating? Yet another radical. That other radical then can continue to react until it neutralizes or reacts with something else. Okay? So radicals are dangerous because those reactions very rarely ever stop. Okay? The only way we can get a radical reaction to stop is by pairing it up with another single electron. Okay? So if we take a look at this last step, what's happening now? We're going to take the radical from our benzene, and we're going to share that with the radical from our magnesium. Okay? And the process, I end up putting 2 electrons into a bond between carbon and magnesium. Okay? And there's our final product of this. What was the whole goal? Why did we go through and do this? Why did we bother to do the Grignard reaction? What was the whole point? What were we trying to make? A nucleophilic carbon, which we could then react with a carbonyl to make an alcohol. Okay? So I need a negatively charged carbon. Does anybody see a negatively charged carbon on this structure? No, so something seems a bit odd. So let's go through and evaluate the bond structure. I'm going to draw that bond out. What kind of bond, I just showed in blue there, between magnesium and bromine? What kind of bond is that? It's a bond between a metal and a nonmetal. Ionic, which means charges. So what charges the bromine then? Charges bromine typically pick up. Negative. See how much you guys remember from your Gen Chem? Magnesium typically picks up what charge? Close. Half right. It is positive. Positive 2. Okay. This overall product that we've got drawn here at the end is neutral. So if bromine's negative and magnesium's positive, what charge does this carbon have to be? Must also be negative. Okay? Why would it be negative? What's the bond between a carbon and a magnesium metal? What type of bond is that? It's a metal and a non-metal. Still ionic. Okay? So we still have those charges showing up. Typically, when you look at Grignard reagents, you tend to ignore the magnesium and the bromine, and we would draw this out. With our negative charge. We now have a nucleophilic carbon. Does it have to be benzene? What if I started with CH3Br? If I react that with magnesium, what's the end result? What would I get? I know those of you listening at home think there's nothing's being said, but it's really vocal in here right now. The magnesium inserts itself between the bromine and the carbon, and in the process, it shuttles the 2 electrons it's got to the carbon, so we can equate this to being CH3 minus and our MgBr, overall positive. Okay? Nothing about the mechanism changes, nothing about the reaction changes. All we're trying to do is make that carbon negative. Okay? If we drew out, let's just erase everything, just because that's fun. Let's draw out one more case. And we reacted this with magnesium. Which carbon becomes negative? The one attached to the bromine. Okay? So if we were going to react this out, we could say we do the magnesium step first. We'll follow that up with acetone. Okay, and then let's be extra mean. Go ahead and throw in that third step of H3O+. Okay. We said our carbon, after the first step, that red carbon becomes our nucleophile. What does our nucleophile react with? What do all nucleophiles react with? I said nucleophile, didn't I? Yes. Yeah. They react with an electrophile or something positive. What's something positive in our step 2?
The carbon.
Okay, the carbon of our carbonyl. So let's predict. What happens to our side groups? There's our electrophilic carbon. We're going to break our pi bond. We put the oxygen up top. What do we attach down below? How do we incorporate these 3 carbons? Where are those bound? Okay. Do I have the red carbon drawn yet? No. So let's draw that first. Okay, what is that red carbon bound to? 2 other carbons, I can accept that. What else is it bound to? Remember, we're reacting it. So it's no longer bound to the bromine. Red was what? Okay, what did it react as? Nucleophile, electrophile? Okay, it's a nucleophile. Okay, well, apparently that example sucks, so let's not look at that example. Let's just attempt to move on to another one. Whoa. If I can move on to another one. We will look at examples here in just a little bit. Then we'll go through a couple of those, but before we do that, because we lost all that work anyway, solvent role. Our solvent needs to stabilize our reactive intermediate. Okay? So our reactive intermediate was ultimately our negatively charged carbon. Okay? And officially our positively charged magnesium and our negatively charged bromine. What kind of solvent would stabilize those charges? A polar solvent or a non-polar solvent? Has to be polar. Okay? The polar would generate partial charges. Those partial charges could match up with the partial charges or the formal charges of our reagent and stabilize them temporarily. Okay? Now the next part. What's our next classification? We've got, whoops, draw this a little bit higher. Our initial classification is polar and non-polar. We can take that a step further into aprotic and protic. Okay. Aprotic meant what? No hydrogens, no hydrogen bonding. So no hydrogens bound to oxygen or nitrogen. A protic solvent would have hydrogen bound to oxygen or nitrogen. Okay. Which one of those should we use? Okay. If we used a protic solvent, let's kind of push it to the extreme. What's the most protic we could get? Something that's going to be willing to donate hydrogens, right? Okay, so we could go with something like water. I was going to take it even further than that. Because protic ultimately just means that we have H+. How else can we get H+? There we go, HCl. Doesn't get more protic than HCl. Okay? We have a very positive hydrogen. Is HCl something you typically want splashed in your face? No, highly, highly reactive. So we want to stabilize that positive as best we can. Do we have a negative in our Grignard reagent? The carbon was a negative. What's the issue if we add a protic solvent? They react. The negative of our Grignard reacts with the positive of the hydrogen. What happens? You form a bond. What's the issue with forming a bond? Change the structure. Do we have a negative carbon anymore? No, we would have neutralized it. Okay? So our Grignard reagents are great for generating a good, strong nucleophile. Okay? What's the definition of our nucleophile? An electron donor. What other species are electron donors? Bronsted bases. So our Grignard reagents, while they may be great as nucleophiles, they're very limited in their reactivity because they can act as a Bronsted base. So we must limit the presence of protic solvents or acidic hydrogens. So when we're looking for an ideal solvent for a Grignard, it is a polar aprotic solvent. Okay? So when you run a reaction, make sure that you don't have anything acidic present, because that acidic atom will react with our Grignard preferentially, because acid-base chemistry is much easier to do than our Lewis acid-base chemistry or our nucleophile electrophile stuff, and we end up quenching and ruining our Grignard reagent instead of getting our new bonds. Okay? And yes, we will look at an example of that here in just a second. It's my fault, don't worry about it. So, some reactions. So we'll kind of work through a few of these together. Then I'll give you a couple minutes to work on another few of them and see what can happen. So the very first one, I broke down into individual boxes. So we've got 3 problems here. So I know that can be difficult to classify sometimes. So we've got, 4 problems. 1, 2, 3, 4 problems. Okay. So in our very first one, like I said, it's nicely broken down into individual steps. In our very first step, what's our product going to be? What should we draw within that box? The magnesium needs to be between the carbon and the bromine. There we go. How many carbons is that? I know it seems like a silly question, but it's really easy to lose carbons. How many carbons? 2. Okay, what happens in the next step? Okay. Our carbon, where the magnesium is bound, shouldn't have picked red, is now our nucleophile. What does the nucleophile react with? Something positive. So we can take a look at step 2. Where's the most positive atom in step 2? The carbon of our carbonyl. So that would react as an electrophile. What's the product of this reaction? We're forming a new bond between the nucleophile and the electrophile. So what we'll go through and do is show that new bond. There it is. What else was attached to our nucleophile? Okay, we have one more carbon attached to it, so there's our 2 carbons from our nucleophile. What about the magnesium and the bromine? Okay, it is very typical for people to draw on MGBR. If you're about to draw that, don't. Okay, why is it a bad idea to draw that bond? Where did the carbon get its electrons? From that bond. So carbon took those electrons to make our new bond between our nucleophile and our electrophile. If it took those electrons, what happens to the bond between the magnesium and the carbon? That's a big eraser. It's no longer there. Okay? And we could go through, for the sake of balancing, and say we've got now a positive magnesium bromide floating around in solution. What else do we need to add to our structure? The oxygen. How is the oxygen connected to the structure? What atom is it connected to? Which carbon? The blue carbon, or our electrophilic carbon. So we can show that bond and draw on our oxygen. Sometimes your drawings don't fit in the box. That's okay. What's that?
It's a one-legged man.
Yeah. The pi bond is lost in the process of this reaction. If you didn't remove it, how many bonds would our electrophile have, the blue carbon? It would have too many bonds. So we had to break that bond to form our new bond. How many electrons would be around that oxygen? We've got 6 electrons, which means it is negatively charged. At this point, if we wanted to, we could connect the positive magnesium to the negative oxygen. What type of bond is that? Ionic. So is that really that important of a bond to draw out? No. So we don't need to show that if we don't want to. Our reaction stalls at this point. So we add our third reagent, H3O+. What happens? And we end up with our alcohol. Nope. Okay, and yes, it's our one-legged man. Okay, questions about how we broke that down? Okay, I'm going to give you 5 minutes to work on the last 3. And then what I'm going to do is just draw the answers in there. And we'll talk about 4. But we're just going to draw the answers in for 2 and 3. Okay, we'll go ahead and get started again. So number 2, I tried to draw it first off wrong, but then attempted to make it look neat wrong, and that didn't work. One of the more common things that students will miss here, what changed? What's wrong with what's drawn here? There's a couple things wrong with it, actually. How many bonds does that carbon have? That's got way too many bonds. One of the most common mistakes when dealing with Grignard reactions is losing a carbon in the process of the reaction. Okay? So you end up saying, oh, well, the electrophile carbon here bonds to that carbon, and now all of a sudden they become the same thing. Okay? That doesn't happen. So what you should do is go through and count your carbons when running these reactions to make sure. Or, if you can, identify them. Okay? So our triangle is our nucleophilic, and we'll call the box our electrophilic. So when we draw out our product, our box needs to be bound to the triangle. Oops. There's the bond out. There's the triangle atom. The triangle atom is a benzene ring. Does that make sense? I noticed a lot of people were drawing the hydrogen. Is it wrong to draw that hydrogen in there? No. Is it necessary? No. Okay, so it's entirely up to you if you want to draw that in or not. Okay? When we move to the next one, question 3. Question 3 is a little bit tricky because CO2 is drawn out as its formula form as opposed to the structure. When you draw out the structure, you should hopefully see that the carbon in CO2 acts as an exceptionally good electrophilic atom. I guess I should draw that in blue for pattern's sake. Okay. And our Grignard reagent can form a new bond to that, and we generate a carboxylic acid as our product. Okay. We still convert one of the carbonyls into an OH, but we didn't react the other carbonyl, which means it stays. Okay? Question 4. What's the difference between our starting material and our product? Absolutely nothing. What? What happened? Because a reaction did indeed occur. And in fact, maybe to help out with balancing, we can draw in here another product formed was this. Just to make sure we have no confusion on our hydrogens. We also form butane in the course of this reaction. What? Where did the butane come from? That last bond is to what atom? Lithium. Well, that's not a Grignard reagent, right? Now we talked about magnesiums. Okay, what charge is that carbon bound to the lithium? Still negative. It may not be a Grignard reagent in the strictest sense of what we're used to defining as a Grignard reagent, but it is still a negatively charged carbon. Okay? That lithium atom or lithium metal donated its electrons. It got rid of a hydrogen off of our butane, and we end up with a negatively charged carbon. Okay, so we still have that negative carbon nucleophile. Okay? What does that negative carbon want to react with? Something positive. Where's there something positive in my material, or my starting material? What's that? H3O is the second step. What's that carbon? That carbon of the carbonyl is positive. We just looked at that chemistry. So why did the negative not attach to the positive? What functional group is that? Is a carboxylic acid acidic? Yeah. What happens when we react an acid with a strong base? We get an acid-base reaction. This species, our lithium, our butyl lithium reagent, reacts with the acidic hydrogen to form butane. Okay? That would then make that terminal, cactus, oxygen here negative. What do we do in the next step? We add acid. which then puts the hydrogen right back, and what do we end up with? Same thing that we started with. Okay? So when you go through and do Grignard reagents or Grignard reactions, you do need to be aware of the reactivity of the carbonyl carbon. Okay, but that's not the only positive atom. In some cases, you can generate another positive atom or an acidic hydrogen. Okay, this is why we talked about the solvent requirement. We want a polar aprotic solvent. We do not want acids when working with Grignard reagents. Otherwise, we get the acid-base reaction and not our nucleophile, nucleophilic addition. Yes?
We do the hydrogen on the other oxygen.
Yes.
On the product, the pi bonds are different than on all of the.
I think I heard somebody say that. Does it matter? You've got resonance through that pi system, which we haven't talked about yet. The resonance in that ring puts those double bonds equally at every single position. So it doesn't matter how you draw the double bonds in there as long as they're alternating. Yeah, and we'll talk about that next week when we look at chapter 9. Okay? So that's your carbon nucleophiles. Okay, and if you thought that was hard, if you ask me, all the other stuff is harder. Sorry. Okay. Really only have a couple slides when looking at nitrogen as a nucleophile. Okay. Nitrogen already starts out as a pretty good nucleophile. That lone pair works as a base and as a Lewis acid, which is the definition of a nucleophile. Okay. So we can go through and look at how the nitrogen reacts with our carbonyl carbon. And we'll break this down by looking at each of the individual mechanistic steps. What I expect you to be able to do is to move between each of these, but not have the entire thing memorized. Okay? I will not ask a nitrogen nucleophile carbonyl entire mechanism. Individual steps are fair game. Okay? And end results. So, nitrogen, nucleophile. What does our nucleophile want to react with? A partial positive. So we've got our carbon. So what can happen? We'll take the electrons from our nucleophile, react it with our carbon. How many bonds would that carbon have? Too many, so what do we have to do? We'll break a bond by shifting the electrons to the oxygen. Okay? So we're following the same pattern that we've seen with these. So our result... Do I have all the lone pairs? Yep. Okay. Oh. Sorry. Forgot. This is one of the reasons why I'm not going to ask you mechanisms for these. Sorry, I'm about to erase all this. We'll come back to it in a second. That nitrogen acting as a nucleophile, while it is a reasonable nucleophile and the carbon is a reasonable electrophile, it's not a particularly easy reaction. Okay, so it doesn't go in very high yields. So what we're going to do is add a catalyst to this reaction. We're going to add an acid catalyst. That catalyst is going to activate our electrophile and make it more electrophilic. Okay, so we still have our nucleophile in there. And we still have our electrophile. What we're going to do is take the electrons off of our oxygen and react them with the hydrogen. We can then push those electrons over to our water molecule. The result what charge does the oxygen become? Positively charged. Does oxygen want to be positive? Nope. So what happens? It starts to steal electrons from its easiest source. Where's a nice source of electrons? In the pi bond. As those electrons shift up towards the oxygen, what happens to the carbon? It becomes increasingly positive. So by having the acid react with the carbonyl, we can make our electrophile more electrophilic, more susceptible to the nucleophilic attack of our nitrogen. The result is what we would refer to as our tetrahedral intermediate. Why would we call it tetrahedral intermediate? The carbon where all our chemistry is occurring is what hybridization? sp3, which has what shape? Tetrahedral. Okay? Is that structure stable? No. What's wrong with it? Positive on the nitrogen. So how can we fix that? Sorry, what's that?
Find something with electrons or negative charge.
So if we tried to find a negative charge from outside the structure, we're trying to bring up more electrons into the nitrogen, right? How many electrons does the nitrogen have around it currently? It has 8. If we bring in another source of electrons, how many electrons would be around it? 10. Can it have 10 electrons? No. So instead of looking for electrons outside the structure, we must look for electrons within the structure. Where's the easiest place for that nitrogen to steal electrons from? From the hydrogen. So we can take the electrons away from that hydrogen and we end up with our next product. Okay? We're moving this direction. Yes?
Is magnesium and bromine the only time that it moves one electron at a time?
It's the only time that you can expect to see. We're not going to talk about another method. Okay? We now have something that we might consider relatively stable. Okay? There is a problem with this, though. The carbon is sp3 hybridized, which means it's no longer as electronegative as it was initially, okay, where it was sp2 hybridized. Which means when we put those two electronegative elements attached to it, the nitrogen and the oxygen, that carbon really starts to lack electrons. Okay? So it starts to panic a little bit and wants to steal electrons back from something. Okay? So the next sequence of steps are all about facilitating carbon getting more electrons. Okay? So we have to somehow cause some bonds to shift and break to allow for some electrons to come in and stabilize it. Okay? We could have the oxygen share electrons with it, okay? But that takes us right back to the beginning. So ultimately what we're trying to do is to facilitate that nitrogen giving electrons. Don't draw this. If the nitrogen gives in the electrons, how many bonds would be around that carbon? 5. So we would have to break a bond. That would absolutely be the easiest bond to break. But that means we get what as a leaving group? OH minus. Is that a good leaving group? No. So what we have to do before we can do that reaction is get that OH to be a good leaving group. Okay? How can we get it to be a good leaving group? We're going to have it react, whoops, that's an eraser, with our acid catalyst to get protonated. Now when we go through and look at our, oh, I drew it on the other side. Now when we go through and look at our reaction, that oxygen is positively charged. Again, a bad thing. What can that oxygen do to stabilize? It needs to pull electrons or get electrons. We could again look outside the structure, but how many electrons are currently around the oxygen? One lone pair, 3 bonds gives us 8 electrons. So oxygen has its octet satisfied. Can it accept electrons from an outside source? No. We must look within the structure. Where do we have electrons within the structure? We could pull them from the hydrogens, but that takes us backwards. So instead, we'll pull them from the carbon atom that it's attached to. But then that carbon lost a bond. Starts to panic, so what does it do? It will steal electrons from our friendly neighborhood nitrogen. What's our result? So, let's see if I can draw this all out. Okay. Our oxygen gained electrons, started positive, gained electrons, so it's now neutral. Our nitrogen still has that hydrogen attached. Our nitrogen started neutral, lost electrons, so it is now positively charged. Okay. Does nitrogen want to be positive? Nope, so it needs electrons. Where can it get electrons from? It can steal them from the hydrogen. And we'd end up with our final product. This new product is now referred to as an imine. Okay? You're not strictly responsible for knowing that it's an imine. I'm just telling you what it is. What I do expect you to be able to do is to move through each of these mechanistic steps. Okay? When we walked through it, we went through and just kind of predicted at each point. Okay? I didn't go through and have you compare product to starting material to try and figure it out. Okay? On an exam, take advantage of that information. So for instance, if we look in at our middle reactions, if you were just told to provide the arrows to go from right to left in this case, you could just try and guess and say, well, what's reactive in each of these cases and try and figure it out. Or you could compare to the product. What changed? That oxygen picked up a hydrogen. Whatever we do here has to have that oxygen sharing electrons with a hydrogen, because that is the result of this step. How do we know that's the result of the step? Because it's given to you. Okay? Does that kind of make sense? So what you need to be able to evaluate when you do most of the imine reactions, at least as far as the exam is concerned, is if I give you any set within this, you should be able to predict what's going to occur. Okay? I'm more concerned that you're doing things that make sense. For instance, if you'd had the nitrogen donate its electrons in earlier, okay, so if we had drawn out this initial step, I expect you to be able to recognize that OH minus is a terrible leaving group and that those blue arrows do not make sense. You wouldn't show those. Okay? So the idea is to add arrows as appropriate to follow through and make things work as best as possible. Okay? Does that make sense? I know, the nitrogens or nitrogen as a nucleophile is a bit of a stretch. Okay? But remember, I'm not expecting as much when it comes to this. Okay? Questions about this one? Okay? And as we can now start doing with these, why is it relevant? Okay? What if our carbonyl has a leaving group? So if we shift to a different system, if we generate a leaving group on our carbon, that carbon is now extremely positive. If I react it with a second molecule, the nitrogen can swoop in, donate its electrons to that carbonyl. Okay, and this is where carbonyl chemistry can be nice. What's the easiest bond to break? The pi bond, so we could break that. But then what ends up happening later on? We remake it, because we have too many electronegative elements around our individual carbon. What's the easiest bond to break now? Chlorine. Why is chlorine a good bond to break? Because chlorine is a good leaving group. Okay? And we can generate a single bond now between these two structures. Those of you taking the lab, why is this important? What did we just make? I know it's a bit of a stretch. We took 2 units and we made 1 unit. What if we took another unit? Do I still have a reactive nitrogen? Do I still have a reactive carbonyl? Could I add another unit onto this end? And another unit on that end? And so on and so forth? What have we made? A polymer. Okay? Take it a step further. What polymer did we make? Let's change the structures ever so slightly. Instead of it being a chloride, we make it OH minus. Instead of it being CH2 in the middle, I add an R group. What compound is this? It's an amino acid. When I bond that amino acid to another amino acid, what have I made? Proteins. Okay? This is the chemistry that your body does every day. Okay? How can we get this reaction to occur, though? OH minus is a terrible leaving group. This is why biochemistry can be fun. How do we get it to occur? We don't. We make some enzyme biochemistry thing do it for us. Do we have any idea how it works? Probably not. But we just say it does. Okay? There's biochemistry. Yay. Shit, I was recording. Okay? So, that's kind of your application when you're looking at nitrogen as a nucleophile with your carbonyls. Okay? All proteins come back to this chemistry. All amino acids come back to this chemistry. When we look at oxygen as a nucleophile on Wednesday, we're going to look at carbohydrates, which is, and for that matter, I guess DNA as well, which is the next big section as far as biochemistry goes. So the linkages between those carbonyl functional groups ends up showing up in oxygen as a nucleophile. Okay? So I will go ahead and call it